Let's start. We have a red light. Let's quiet down. I'd like to start this class, please. Thank you. So today we want to make the first step towards understanding that. Now, what am I showing you there? I'm showing you the price of something which is going to play the role of an underlying asset for us. In this case, this is the share price of British Petroleum shares over a time period. This is from the late 80s until now. And the horizontal axis here is time, the vertical axis is price, and we see the price going up and then going down and up and down and up and down. And I want you to compare this with this very simple model of price evolution that we had last time. Remember, we lived in a world in which we observe a price, and then after some discrete period of time, the price goes up or the price goes down. This doesn't look like that. This is a much more complicated world, and our aim is to understand that world. Now, maybe you're thinking, well, this is a very long period of time. We're looking over 30 years. Maybe if we concentrate on a shorter period of time, we can see some nice things that look like this. Either the price goes up by something or the price goes down by something. So let's see if I can give you some evidence that that's not the case. So let's look at the price over a 1 month period, and let's have a look at let's take 10 days, and let's have a look at 1 minute periods. And the line looks just as jagged as it did before. So now instead of looking at 30 years on daily data, now we're looking at 10 days on minute by minute data, and the world doesn't seem to be getting any simpler. We're getting this very jagged, complicated curve, which at some point we want to understand. And how we're going to understand this? Well, we're going to get inspiration from physics, so we're going to look at Brownian motion, and that's going to solve the problem for us. So here's Brownian motion. So what do we see here? We see some particles suspended in some liquid or some gas, and they jiggle up and they jiggle down and they jiggle up and jiggle down. And we're going to use the same mathematics which explain this physical phenomenon. We're going to use essentially the same mathematics to understand the jiggling up and down of prices of things. Okay? Now to do that we have to understand probability. And I don't trust your understanding of probability. So what I'm going to do is I'm going to remind you of probability. So here's a speedy review of all the probability that we're going to do in this course. Now, this is important. We're getting to the climax of our course, and the climax of our course is difficult. It's difficult because it requires you to understand some serious mathematics. In this case, it's going to be serious probability. So look at what I'm going to show you today. If anything here doesn't ring a bell, then you have to put some work into this. Otherwise, you're not going to understand what comes next. All right? So let's start with the beginning. And the beginning is the definition of a probability space. What is a probability space? So at this stage, I'm just telling you it's a triple of things. So we have a set, which I'm going to call omega. And then we're going to have another set, F, which is a collection of subsets of omega. And I have a function, P, which takes values at elements in F and gives you a number between 0 and 1. And this function has some properties. P of the empty set is 0. P of the whole set of omega, which is a subset of itself, is 1. And if you look at a disjoint collection of sets in F, and if you look at the P of the union of this disjoint collection of sets, what you're getting is the sum of the P's of each one of the elements in this set. Now, what is this? What am I talking about? So let's think about making an experiment. The experiment can be, I don't know, measuring something. and then the set of all possible outcomes of the experiment is what I'm calling omega. So think of omega as the set of all the things that can be observed in your experiment. F then is a set of events. So if the experiment is to measure someone's height, then we can say, let's talk about the event in which the measurement is bigger than 6 feet. That's an event. So that's an example of a subset of all the possible elements in omega. It's a subset of omega. You can have all sorts of measurements. You can measure 1 foot and 10 feet and things like that. So I just gave you an example of this, the subset of omega consisting of all the measurements which are above 6 feet. And what is P then? Well, once we talk about events, the event of these things coming as an outcome of an experiment, we want to assign probabilities to this. And this is what this probability function does for us. So you take an event, you look at P of that event, and then you get the probability. Okay, so that's the formal definition of a probability space. I really, really hope that this is ringing bells. If not, then I'm going to give you some examples next. Maybe that's going to help us. And if not, if we still are clueless, then we should go back and review this material. So let me give you some examples. So let's start with an experiment, which is going to have a set of outcomes. And our experiment is tossing 2 fair coins and observing what happens. So we can ask ourselves, what's the experiment of tossing these 2 coins, coin number 1, coin number 2? Then the set of all outcomes is what I'm calling omega, and there are 4 possible outcomes: heads, heads, and heads, tails, and tails, heads, and tails, tails. And now, in this case, I'm going to give you a set of events, which is going to be anything you can think of. So let's take the set of events to be all the subsets of omega. How many subsets of omega we have? So we're talking about a set of 4 elements. Each time when I construct a subset, I can either choose or not choose to include any of the elements. So I'm choosing 4 times among a choice of 2 things, to include or not to include. So we have 2 to the 4, 16 subsets of omega, and each one of them is going to be an element in what I'm calling F. And now, to make this into a probability space, so I told you what omega is, I told you what F is. To make this into a probability space, I have to assign probabilities to every single event in F. And how am I going to do that? So I'm going to describe a function from the set, in this particular case, the sets of all the subsets of omega to the numbers between 0 and 1, which satisfy the condition in the previous slide. And the way I'm going to do that, in this case, if I want to model tossing 2 independent fair coins, is going to be, give me an event, A, right? So say the event that the first coin is heads, so I'm talking about heads, and heads, tails. Count how many elements are in your event, and then assume that every event has the same probability. In other words, take the number of elements in your event, the number of outcomes of your experiment in your event, and divide by the total number of possible outcomes. In which case, in this case, is 4. So if we define P of A to be this fraction over there, we get what we would expect to be the probability of an event under the assumption that the 2 coins are fair and independent. Okay? So, now that we've seen the definition of probability spaces, and now that I'm telling you that this omega and that F and that P form a probability space, is this making sense? Does this look familiar? Okay. So this is the kind of things that we want to understand. Now, maybe when you did probability, you just roll up your sleeves and you didn't worry about the definitions of probability spaces, and you just went ahead and computed probabilities of things without doing things formally. But now, next week, no, actually not next week, next lecture, we're going to start doing some very intricate probability modeling, and then we're going to have to know what we're talking about. So we need to know what these probability spaces are. Let me give you another example, and here things are a bit more complicated. So let's look at a uniform distribution in the interval 0, 1. So what do I want? My set of outcomes now, think of making an experiment and choosing a random number, a random real number between 0 and 1. So now my set omega is going to be the set of all the real numbers between 0 and 1. And then I want to define a set of events, and I want to define a probability on these events. And what I want is that if I ask myself, what's the probability of the event A, B, when A and B are between 0 and 1. So what does this say? This is saying, what's the probability of picking a number between A and B? So we want this to be B minus A. Right? So can we do that? Well, it looks as if I've just done it, but what's missing here? What's missing here is I have to tell you what is a valid event, to which events are going to be assigned a probability. You can say, well, just give a probability to any event. Well, you can't. There is a theorem that says there is no way to assign probabilities to any subset of omega so that this probability function is a probability function. Now, we're not going to go there. I'm just telling you this so that you are aware that there is something interesting going on here. And then how do you solve this problem? How do you come with a probability on subsets of omega? So first you have to choose your collection of subsets of omega very carefully. And you can do that. There is a smallest F, the smallest collection of events, which contains all these intervals and which is closed under countable union and intersection. And then for this special family of subsets of 0, 1 of omega, you can assign probabilities. So you can construct a family of subsets of omega which contains all these intervals, and it contains many, many, many other things. And then, at least for these intervals, you get the right probability. You can define a function on F so that P of that interval is B minus A. So that's another example of a probability space. It's a complicated example. I'm telling you there is an F in our definition of omega Fp. I'm not telling you what this F is, and I'm not telling you what this F is, because even in this simple example, you end up with a complicated answer. Those of you taking the course on stochastic processes, this is a Borel family of sets. So you may have seen that there. Okay, does this example look vaguely familiar? Random, uniform distributions on the interval 0, 1. Okay, that's a formal way of thinking about these things. Okay, so now we know what probability spaces are. They look like this, these triples. The set of outcomes of an experiment, the set of events for which we're going to assign probability, and the probability function defined on F. And now I'm going to tell you what the random variable is. And this comes to a surprise to my class every single time I show this. What is a random variable on a probability space? It's a function. It's a function from omega to the real numbers. So it's a function which eats outcomes of an experiment, and it gives you a number. This is what x does. But it's not just any function. It has to be compatible with your set of events. So the way I'm saying it there is to say that x inverse of the interval from minus infinity to a is an event, which is another way of saying, if you look at the event x is less than a, which is just another way of saying x inverse of minus infinity a, this is an event. An event for all a, which means that you can talk about the probability of your random variable x being less than a, i.e. P of the event x less than a, which is the kind of things that you look at when you do probability, is defined. Okay? Now, here's what people find surprising. Random variables are not random, and they're not variables. Random variables are functions. Okay? Okay, does this look familiar? Very good. So now let's move on and let's define some random variables. So let's go back to the first example I gave you. So we were tossing two coins. We had a set omega consisting of 4 outcomes. And now I can say x of omega, I'm defining a random variable on that probability space. And how do I define it? I have to give you a function x from omega to the real numbers. And then I say, okay, x of something is the number of heads in that outcome. Right? So let's see. X of HH, right? HH is an element in omega. It's an outcome of the experiment. This is 2. And x of HT, which is another outcome of our experiment of tossing two coins, is going to be 1. Okay, so that's a function. And you can convince yourself that all these events are well defined, that the probability of these events is well defined because we define the probability of any subset of omega, any one of the 16 subsets of omega. So x is not just a function, it's a random variable. And now we can ask all sorts of questions. For example, what is p, the probability of x inverse of 1? So I'm talking about the probability of the event x equals 1. So there are two ways in which x is going to be 1. It gets the value 1 with heads, tails, and tails, heads. There are two such events. The way we define probabilities, the probability of this event is 2/4, which is 1/2. Okay? Now, the calculation of the probabilities here is pretty trivial. What's not trivial here is to notice the relationship between what I'm showing you, between these very simple examples and the various concepts we started with. Probability spaces, random variables. We have to keep track of that because very soon things are going to be more complicated. Okay? So, do you see the connection between this and the definition I gave you of a random variable? Hello? If you say no, I'll explain. Fine. And now let's go back to the second example and let's define another function from omega to the real numbers. So you give me an omega in the second example. What is an omega in the second example? A little omega in the second example. It's a real number between 0 and 1. I say x of omega is omega squared plus 1. Why omega squared plus 1? Why not? So, okay, that's a function from omega to the real numbers. Is it a random variable? What do I have to check to make sure that this is a random variable? I have to check that x less than a is an event. In other words, I have to ask myself, what sort of set is the set of all the omega squared plus 1 such that the set of all the omega, so that omega squared plus 1 is less than a, then you're going to say, okay, so that's the same thing as omega squared is less than a plus 1, and then what you're going to get is that omega is between, unless it, okay, this is not going to be, let's take a to be greater or equal to 0, and then omega is going to be something of the form the square root of a minus the square root of a plus 1 and plus the square root of a plus 1. And what's so great about this? Well, this is one of our events. Okay, this was one of the sets which we declared to be an event, an element in F, and this you can obtain it by taking complements of other sets which are events. So don't want to go into the details of this, but this is this event, the set of all the omegas for which this is happening. This is a Borel set, which is another way of saying this is an element in F. This is an element for which you can define probability, a uniform distribution probability. Okay, again, I don't want to go into the details of this. All I'm saying is that here's an example of a random variable, and you should be able to connect what I'm showing you here with the definition of random variables. Okay. What else do we want to say about probability spaces? Well, probability spaces come in two flavors. There are discrete probability spaces, and when I say that, I mean that omega is either finite or countable. So here's an example of a finite omega, a finite set of outcomes of an experiment, for example, or countable. So here's how I'm going to write a countable set. And when your omega is discrete and you're asking yourself what events are going to have a probability associated with them, you normally are thinking of all the subsets of omega. So you're going to assign probability to any event which is a subset of omega. And now, as I said before, if your probability space is not one of these, if it's not discrete, this is not always possible. So going back to the examples we've seen so far, the first example with the two coins being tossed is an example of a discrete probability space. Omega at just 4 elements. And example number 2 was not an example of a discrete probability space because this is not finite or countable. It's an uncountable set of outcomes. All right. Another thing we need to know is the concept of independent random variables. So let's have a look at random variables defined in the same probability space. So we have x1 and x2 up to xn. Each one of them is a function from some omega to the real numbers. They all share the same omega. And we're going to call this independent if for any numbers a1 up to an, you can talk about this event. So you can talk about, let's write this in terms of omegas. What's written on the left-hand side there, I'm talking about a subset of omega. I'm talking about P of all the omegas for which x1 of this omega is less than a1, and x2 of that omega is less than a2, and so on, up to xn of that omega is less than an. So P of this set over here can be written as a product. The product of what? So now I concentrate on each one of these events, the probability of xi being less than ai. Each one of them is going to be an event as well. How do I know that? Because each xi is a random variable. And now I'm going to take the product of all of these. And I demand that these two are the same. So if this happens for all choices of a1 up to an, then we call these random variables independent. Okay? So you can read this in English, and you can say the probability that x1 is less than a1, and the probability, and that x2 is less than a2, and so on. It's the same as the product of the probabilities of x1 being less than a1, and x2 being less than a2, and so on. So again, I believe that you've seen this concept before. I just want to make sure that you know what I'm talking about when I say independent random variables. Okay, so now let's associate some numbers with random variables. So the first one is going to be the expected value, or the average, if you prefer, of a random variable. And we're going to do this in two cases. The first case is the case of a discrete random variable, so a random variable defined on a discrete probability space. And then what we do is we take the weighted average of the values of your random variable. So you go over all the possible little omegas in big omega, and you look at x of those omegas. And you take the weighted average of all these values of x, weighted by the probability that omega happens. And now, if omega is finite, you have a finite sum, which is fine. If omega is not finite, you may have an infinite sum here, and then you have to worry whether this infinite sum converges absolutely, that is, regardless of which order you add your summands. And if this sum here converges absolutely, you declare this weighted average of the values of x to be the expected value of your random variable x. Now again, I believe that you've seen this, so I'm not going to say much more about this. But let's have a look at a quick example. So let's have a look at tossing fair dice. So now we have a probability space in which omega contains 6 possible outcomes corresponding to the 6 faces of the die. We can take all the subsets of omega to be our f, so we can assign probabilities to every single collection of outcomes of tossing the die. So in this case, we're going to have 2 to the 6 of these, 64 of these. And now let's define what the fair die is. We can say, if you want to know what is the probability of E, of the event E, well, count how many elements you have in E and divide by 6. That's another way of saying all outcomes are equally likely. And now I can start defining all sorts of random variables in this. For example, I can define x of omega to be omega, and I can define y of omega to be omega squared, and then we can talk about the expected value of x. So it's the weighted average of the values of omega weighted by the probability. The probability is always a 6. So we're getting this number over here, and I can also compute the weighted average of the values of not the number on the face, but the number of the face squared, and I get this other number. Okay, so that's an example of computing expected values. Here's an exercise for you. If I give you 2 random variables defined on the same probability space, and if I give you 2 real numbers, lambda and mu, I can talk about a new random variable, a new function from omega to the real numbers, which has a nice property, and that new function is going to be lambda x plus mu y. Right? Each one of them is a function, x and y, both are functions from omega to the real numbers. Here's another function from omega to the real numbers. You can ask yourself, what is the expected value of this new function on omega, this new random variable, and you're going to get this. So let's read this in English. This is saying the expected value of a linear combination of 2 random variables is the linear combination of the expected values of the random variables. In other words, the expected value operation is a linear operation. Okay, so this is how we define expected values for discrete random variables. What do we do with random variables which are not discrete? So to make sense of this, we have to introduce density functions. So what is a density function? So if you give me a random variable and I claim that this function f from the real numbers to the non-negative numbers is a density function, what I'm saying is that if you want to know what's the probability of x being less than a for any choice of a, what you need to do is you have to take this function f, and integrate the function from minus infinity to a. Okay? So how does it look like? It looks like this. Let's take, for those of you who know, a normally distributed random variable, which is going to have some density function of this form. So here is going to be the density axis, density, and here is going to be an x. And if you want to know what's the probability of x being less than a little x, then you put your little x here, you take your function, you integrate from minus infinity to x. In other words, you're looking at the area under the graph up to this point over here, up to this x, and that's how you measure the probability. And so you can ask yourself which functions can play the role of being density functions. The answer is any function whose integral from minus infinity to infinity is 1. And you can now also define the distribution function of a random variable, which has density function f, and that's a probability that your random variable is less than x. So this is what we call f of x. That's a distribution function, which is the integral of the density function. So just to make sure that you know what I'm talking about, does this ring any bells? Are we happy with this? Okay. And now I can define the expected value for random variable x. So instead of taking a weighted sum, I'm going to take a weighted integral. So the expected value of x is going to be the integral of t f of t, when f is the density function of x, and I integrate this over all the possible values of the random variable, that is from minus infinity to infinity. And then you can do something else. So if you want to know the expected value of a function of a random variable, which is a new random variable, you can compute this integral, and that's going to be the answer. Okay, what else do we need to know? We need to know about variance and covariance and correlation. And here's the definition of the variance of a random variable. So what's that? It's the expected value of your random variable minus the average of your random variable squared. So it's the average value of the square of the distance between your random variable and its average. That's what it is. And now you can take this definition, you can take this definition and you can simplify this a bit. You can expand this square, and you can use the fact that the E operation is linear, and after you do that, some things are going to cancel, and you can rewrite the definition of the variance of x as the expected value of the square minus the square of the expected value. And once we know what the variance of a random variable is, we can define the standard deviation of a random variable, which is going to be the square root of the variance. So now let me give you some exercises, and go over these exercises when you go home, just to make sure that we know what we're talking about here. So if I give you a random variable and the number c, and I ask you what's the variance of c times a random variable x, the answer is c squared times the variance of x. And if I give you a random variable and I produce a new random variable, which you obtain by taking your random variable x and subtracting from it its expected value and dividing by its standard deviation, you're going to get a new random variable, whose expected value is 0 and variance is 1. It's a normalized version of x. All right? Does this look familiar? Are we happy with this? Okay. And now I want to talk about the covariance between random variables. And here's how we define covariance. So we look at x minus its average, and we look at y minus its average, and we multiply these two, and then we take the expected value of that. Now this looks really weird until you think about this for a while. And the first thing you can do is you can simplify this. You can expand this and compute variances of various things, and you're going to end up with this other way of thinking about covariances, which right away tells you that if you take x to be the same as y, the covariance of x with itself is, starts with a v, it's the variance of x, because covar xx is e of x squared minus e of x squared minus e of x squared, which is how we define the variance of x. But why do I worry about covariances? Because I want to know what's the variance of a sum of random variables. So suppose that I give you two random variables defined in the same probability space, and I ask you what's the variance of a sum, then your answer should be, if you haven't seen this before, your answer should be, it depends, right? It depends how these two random variables are related to each other. For example, in one extreme, you can take the random variable x and the random variable y, which happens to be minus x, and then you look at x plus y, which is a random variable which is constantly 0, and you ask yourself what's the variance of a random variable which is constantly equal to 0, and that's going to be 0. So in this case, the variance of x plus y is 0. Or you can take x, and you can take y, which is the same thing as x. And now you ask yourself, what's the variance of x plus y? Well, now you're going to get 4 times the variance of x, which is normally not going to be 0. Okay, so you need to know how x and y behave together. And this is what the covariance does for you, because we have this formula that says if you want to know what is the variance of x plus y, well, it's the variance of x plus the variance of y plus another term. And that is the term that measures how x and y relate to each other, which is the term 2 times the covariance between x and y. Okay? Is this making sense? Gosh, everything makes sense today. That's great. That was a joke, by the way. Okay, so what sort of things can we say about covariances? I claim it's a bilinear function in the sense that if you take the covariance of a linear combination of two random variables in Z, well, we're going to get the linear combination of the covariances. And the same thing if you put a linear combination of random variables in the second variable. Covariances of x into linear combination, it's a linear combination of the covariances. And here's an interesting problem for you to ponder. And if you, here's another interesting problem for you to ponder. If adding a constant to a random variable does not change its covariance with other random variables. And this is useful if you try to understand what comes next, which is the notion of the correlation between random variables. So here's the definition of it. What's the correlation rho between x and y? It's the covariance between x and y normalized in some sense. It's the covariance between x and y divided by the product of the standard deviations of x and y. And why do I claim that this is a normalized covariance? Because the correlations you're getting are always numbers between -1 and 1. And if we have a correlation of 1 or -1, that means that one of the random variables is just a linear function of the other one. Okay. And if you go through the exercise here, you're going to see why these statements are true. Okay, so now let's go back to the variance of a sum of two random variables, to the variance of x plus y. And we said we can write this as the variance of x plus the variance of y plus twice the covariance between x and y. And now I want to write this expression in terms of correlations, not covariances. So I take the covariance between x and y and I replace it with the correlation between x and y times the product of the standard deviations of x and y. So I can write it like that. Okay? We're going to be using this formula again and again towards the end of the course when we look at portfolio theory. Okay, what else do we need to know? We need to know about normal distributions. So what is a normally distributed random variable with mean mu and variance sigma squared? Well, it's a random variable whose density function happens to be this one over here. So e to this expression divided by this constant over here. So if you want to know what's the probability of your normally distributed random variable with mean mu and variance sigma squared to be between a and b, what you have to do is you have to integrate this density function between a and b, which is what I've done here. And then if you want to talk about the distribution function, so this distribution function I'm calling n at the value x, at x, well, that's going to be the integral of the density function from -infinity to x. And that's the probability that your big X is less or equal to your small x. And now there's a special instance of normally distributed random variables, which all the other ones can be reduced to. And that's the case in which your normally distributed random variable has a mean of 0 and a variance of 1. We call this standard normal distribution, standard normally distributed random variables. And in that case, the distribution function simplifies. I'm taking mu to be 0, sigma to be 1, and I'm getting this expression for this distribution function. And if we go back to the density function of such a standard normally distributed random variable, well, the density function looks like the picture I just erased. So let me do this again. So the vertical axis here is going to be density. If you want f of x, the density function f of x, and here's my x-axis, and the density function is going to be symmetrical with respect to the vertical axis, and it's going to have this bell shape. This is the bell shape. Okay. Which means, among other things, that if you want to find what's the probability of your standard normally distributed random variable being less or equal to x, here's your x. So how do you measure the probability of being less or equal to this little x? Well, it's this area over here. Then one way of doing that is to say, well, look at minus x. Here's minus x. Look at the probability of being less than minus x, which is this area over here. Now, this area over here is the same by symmetry around the vertical axis as this area over here. So you can write this as the total probability 1 minus the area of this, which is the same thing as the area of that. So you get that the probability of being less than little x is the same thing as 1 minus the probability of being less than minus x. And another thing that actually used many times. You had these tables for normally distributed random variables. So what happened when we wanted to find the probability of some normally distributed random variable being less than A? You first normalize your random variable by subtracting the average and dividing by the standard deviation, and then use that value. So you take the value, you want to know what's the probability of your normally distributed random variable being less or equal to A. You take that A, you subtract the mean of X, and you divide by standard deviation, and then you go to the tables and look at the entry for the tables corresponding to that. So if you look at n, if you take n to be the distribution function of a standard normal random variable, then you can find the probability of any event for any normally distributed random variable, standard or not. And there's some confidence intervals associated with random variables, which I don't want to spend much time over. And that's it. So that was a breakneck introduction to probability. If you haven't seen this before, this makes no sense. I'm hoping that you have seen this before, and I just reminded you of all these concepts. And next time, we're going to look at Brownian motion. And we're going to use Brownian motion to model prices.